In this example, we're doing a derivative of an integral. So again, these things should undo each other. But we have to be a little bit careful when the end bound is a function and not just x. So here we have x squared. That is actually a function of x. This is going to make our answer a little bit different. So we have to be a little bit careful. So here we have this integral of e to the root 1 plus t. We cannot anti-differentiate this because we have this square root embedded inside the exponential function. We don't have a way to anti-differentiate this. But we do know that an antiderivative does exist. So we know that that antiderivative, which is we're just going to call big F, we know that big F exists. And we can evaluate it from x, so from 0 to the endpoint x squared. Okay, well, we're going to evaluate it. So we end up with this is equal to the derivative of whatever we get here. And so we're going to end up with f. I'm going to plug in my x squared into my bound. And I'm going to plug in 0 into there as well. Okay, no problem. This seems very similar to what we did already. But when I differentiate this, okay, I'm going to differentiate big F. That's no problem. That's just little f. But when we differentiate big F, we have little f with an embedded function. Since it's an embedded function I'm differentiating, well, I have rules around that, and I have to apply chain rule here. So I have to remember that I'm going to end up with a times 2x. Well, that f is what we started with. So, and this is going to be minus 0. I'm just going to put a minus 0 in here because that's going to differentiate to 0. We have to remember that. And f, if we recall, that's what we started with. That's going to be this function here. So this ends up being e to the square root 1 plus, well, I had to put the x squared as my bound. Okay, so it gets inside there. But because that x squared was an embedded function, I have to remember to apply chain rule. So these ones here, we have to remember that if the endpoint is a function itself, we have to embed that function into our t and then make sure we account for that with the chain rule because it is an embedded function. So we multiply that by the derivative of that function. So we can show proof of this as well. So if we take a look at when we have an embedded function like that, we know that as we anti-differentiate f, we get the big F function. And we're going to plug in our bounds from a to some function that is g of x. Okay. I'm going to evaluate that integral. So d over dx. That integral is evaluated when I plug in my g of x as one bound minus my a as the other bound. Okay, when I differentiate this, the derivative of big F is going to be little f. I'm back to where I started. So I'm using the fundamental theorem of calculus. The derivative and antiderivative undo each other. So notice that I'm back to that f. But now I have this embedded g of x function. So I need to make sure that I apply the chain rule because I have this embedded function. So I'm going to multiply that by the derivative g prime. So when I have an endpoint that is a function itself, I need to remember to embed that function into where the t was and multiply by the derivative. I'm just cleaning that up here. This should have been, there's a typo here. That should be t here. Okay, so There it is. There's the proof of why we need to apply the chain rule and multiply by g prime at the end.